Hi friends, a very good evening, and could you please confirm in the chat window if you are able to see my screen and hear my voice so that we know that everything is working as expected. So could you please confirm that in the chat window so that I know for sure that things are working as expected. Yeah, I can hear myself in the feedback loop and things seem to be working as expected. Okay, so everything looks good. I also have the chat window here, so that's good news. Let's wait for 3 more minutes because it is 6:57 right now. We'll start the session at 7 p.m. sharp, right? Okay, sounds good. So let's wait for a couple of minutes so that everybody joins. And just for your information, today's session is going to be slightly longer because we wanted to cover more problems today. We have about 13 problems and we will spend about 90 minutes solving them. Typically, we have 8 to 10 problems that we try to finish in 60 minutes. Today, we thought we'll cover more problems because theory of computation is very easy to score marks in, right? So we thought we'll cover especially these topics of finite automata, regular languages, regular expressions, regular grammars, very easy to score marks in, right? So anyway, sounds good. Let's wait for a couple of minutes, and if possible, I can take a couple of questions also. I can take probably one question and answer, but we'll start the session itself at 7 p.m. sharp. If there is any question, do let me know. I'll try to answer that in the next couple of minutes. Okay, everybody can hear. I have these questions here. Okay, good. Sounds good. So I don't see any question till now in the chat window. People have confirmed that they can hear and see my screen and hear my audio clearly. That's okay. We'll start in a minute or so. Best way to prepare mathematics, again, there is no difference between mathematics and any other subject. It's extremely scoring, both engineering mathematics and discrete mathematics. The standard steps are the same, right? Don't go too deep into proofs. Try to get an understanding of the proof, because in GATE, because it's an objective type question paper, you don't have proofs like in a typical non-objective exam at universities, right? So, but you have to understand the concept behind the proof. For example, if you have pumping lemma for regular languages, you have to understand the concept so that if somebody gives you a slightly tricky question, you can figure out whether it is whether the language is regular or not. So you need to understand that, but except for that, the preparation is more or less the same. So 2021 test series, we are almost finalizing it. Hopefully we should launch it next week, right? I think we mentioned to everyone in multiple live sessions that we'll be launching it in early June. So most likely next week. We are just collating all the questions, making sure there are no errors and things like that. So we just want to make sure that the errors are minimized before we launch the test series itself. Best way to solve questions and remember concepts on time complexity. How to prepare undecidability? That's a good question actually. I'll touch upon undecidability a little later when we do future sessions. Like this is the first session where we're mostly focusing on the early topics in TOC. I'll answer that question in one of the future live sessions when we will touch upon undecidability. I think that's the trickiest part of all. So somebody asked this question about best way to solve and remember concepts in time complexity. Again, mostly the hard ones are even in terms of time complexity is just about writing the recursive formulation and applying master theorem or some version of modified version of master theorem, right? So the concepts are not very hard. Again, time complexity questions are often very easy in general because you either have it in simple for loops or you have recursion. That's all, right? So they're typically easy. So when you're learning the concepts, make notes, practice. There are no shortcuts here. Like if there was a shortcut, I would explain you, right? So how to construct minimum DFA for different problems? Again, there is a very simple method where you draw the transition table and try to combine states. I think we have some problems of that sort in today's session. I'll explain you that. but it should be straightforward, right? It's a standard method that you have. Just follow that method. I think we have a couple of questions in today's session also. We'll touch upon that. Okay, sounds good. Oh, it's 7:02, so let's get started. Okay, so before we go in, let me just give you a brief overview of why TOC is a very important subject. And again, just to be clear, we will do a few sessions on TOC followed by compiler design, right? So we want to finish TOC and compiler design, and there is a reasoning behind it. In today's session, we'll focus on these topics only. Typically finite automata, regular languages, regular expressions, and regular grammars. And most importantly, TOC and compiler design are extremely scoring subjects. The problems are typically easier than other subjects. So we have done this analysis and published a video on this. This video is there on our YouTube channel. You can check it out. It's called How to Score Maximum Marks in Theory of Computation and Compiler Design. Right? It's something that we published sometime middle of last year, and we have analyzed almost multiple question papers, multiple sets from the last 5-6 years. And from our observation, typically TOC is very easy to score. If you know the concepts, more than 90% of questions in TOC are easy, right? They're not even there might be one odd question which is tricky, but most of them are easy. Only some questions in undecidability are tricky. But otherwise, again, undecidability is like typically 1 to 2 marks. But typically TOC is very easy to score. And we focused specifically on these topics because almost 50%, almost 4 to 5 marks in GATE typically come from just these topics. There are another 3 marks to 4 marks which come from context-free grammars, PDAs, etc., and 1 or 2 marks from undecidability. That's a typical breakdown. And 50% of the weightage typically in TOC come from just these topics, right? So if you see historically, TOC itself has about 8 to 9 marks, sometimes even 10 marks. So you can think of roughly 8 to 9 marks, of which 4 to 5 marks you can score by just focusing on these topics. It's a very easy to score subject, and mathematically also it's very simple. And all the questions that we will discuss today are typically at GATE level. There are 1 or 2 tricky questions, but most of them are at GATE level. And in this session, instead of doing 8 or 10 questions, we are doing slightly more because these questions are typically easy. So it might take us about 90 minutes. I know some of you might have prepared for only 60-minute session, but we thought since these list of topics are very easy to score, let's solve 13 questions. It might take us more time, but you will be more confident by the end of it, right? Again, we also have some of our mentors who have joined on the chat who will answer some of the questions, which I may not be able to answer due to time constraints. Okay, so let's go to the first question. Okay, so here is the first question. Very simple question. Please take a shot at it. Again, I'm not starting a timer. As soon as I see a few students answering the questions, I'll go and explain the answer. Again, please understand that TOC is typically very easy. Most of these questions are sort of like GATE level questions. So it's very easy to score. Okay, I see a lot of people putting in the answer. So let's take another 10 seconds and then I'll go into the explanation. It's a very simple problem actually. I see a few of you who got it wrong. Hopefully it will be clarified after I explain. Okay, so let's go into the solution. It's very simple. So remember, this is a power n, b power n, but n is restricted because n lies between 0 to 2021, which makes this language finite, right? The number of words that you have that belong to this language is finite, and every finite language is regular, right? So obviously this is regular, right? All finite languages are regular because you can build a finite automata to accept that language. Now similarly, look at this, a power 2n, right? What is a power 2n? What all strings will be there here? Epsilon will be there, AA will be there, 4 A's will be there, 6 A's, and so on and so forth. Again, you can think about it in two ways. It's very simple to construct a finite automata for this, or you can also think of it using regular expressions. This is nothing but A star, right? The moment you have a regular expression or a finite automata, you know that it's a regular language. Very simple. Okay, next comes this. Again, intentionally we have given an easy problem. This is an example that we discuss in our course videos. Let me just show you that. Actually, we discuss when we learn about pumping lemma for regular languages. We explain the whole theorem. We solve a lot of problems, and we also introduce a special case of pumping lemma for regular languages. And we actually show that a power p where p is prime is non-regular language. Okay, so one very interesting theorem here is, imagine if your alphabet consists of only one symbol. Okay, so your alphabet is a singleton set. If your alphabet is a singleton set, it's a very interesting property that your language L, imagine if your language L consists of, has strings. So if the lengths of strings, okay, so lengths, okay, let me just show you in the video itself. I have written it in the video also very clearly. So let me just put that here. Okay, so there is a special case of pumping lemma where the alphabet itself is a singleton set. When the alphabet itself is a singleton set, if the lengths of strings, look at this, the lengths of strings must follow arithmetic progression for a language to be a regular language. And I also explain why this is true by just using the pumping lemma. So this is called the special case of pumping lemma when the alphabet itself consists of only one symbol. Right? In such a case, this is a very nice result that you can arrive at, and in the course videos I also explain how this is justified from the proper pumping lemma for regular languages concept itself. Right? So if you notice this, again, this is a very important property. It's a very important property which helps you solve problems like these better. So if you notice, again, our language is a singleton set. Now if you notice a power p, how many A's will you have? What will be the string lengths? String lengths will be 2, 3, 5, 7, 11, 13, and so on and so forth. So if you see, the gap here is only 1, the gap here is 2, the gap here is 2, the gap here is 4, the gap here is 2. So these string lengths do not follow an arithmetic progression, and hence this cannot be a regular language. Again, you can apply proper pumping lemma for regular languages and prove it, but you can also apply this special case of pumping lemma for regular languages and arrive at the same result. Okay, so this is surely not regular, this is regular, this is regular, so the answer has to be B. Right? Very simple concept here. Right? So the reason we explained this specific property in the course videos and also proven it, or again, we don't prove everything in depth, we try to give you the intuition behind the proof, because in GATE exam you don't require the proofs, but you require the intuition behind the proof. Okay, so very simple question. So let's go to the second question now. Sorry, let me view full screen. Okay, so let's go to the next question now. Okay, here is the second question. This is like a fill in the blank type of question. Okay, I see some variability in answers, so please check. Some people are saying 4, some people are saying 5, so just think through it carefully. Oh, somebody is also saying 6 and 7. So the alphabet is binary, 0 or 1, and all strings except 1, 1 and 111. Okay, I see a lot of answers. So let's go into the solution. Again, we know that some students will make the mistake here. So let's go through it step by step. Again, if there is an error in my explanation, please correct me. So, okay, so this is our language. So if you take the complement of this language, what is the complement of this language? The complement of this language is, again, that's the easy way. Sometimes when you want to build a finite automata, you can build the finite automata for the complement of the language and then build a finite automata that accepts this language. So let's go that route. So what is the complement of this language? LC or L dash. It is basically all the strings W such that strings made of zeros and ones such that W equals to 1 1 or W equals to 111, right? Only these two strings will be there. So this is basically 1 1 or 111. That's all is the language. This is L complement. This is L. L complement is the whole sigma star minus L, right? So that's what it is. So let's draw the finite automata for this first, for L complement. And that should be straightforward, right? So we start at Q0. We should accept 1 1 or 111. Right? So certainly this is not the final state. So if you get 1, and we want to draw a deterministic finite automata, right? Not an NFA. So let's be careful there. So 1 1, right? So if it has 1 1, certainly this should be the final state. Or if you have 1 1 followed by another 1, so 111 or 111, so you get two final states here. Now, what if you get anything except 1 1 or 111, which means in this state, if you get a 0, then you should not go to any of these states. This state basically says that I have seen two consecutive ones or exactly 2 1s. This state basically says I have seen exactly 3 1s. So this should go to another state here. Look at this. Sorry, this is the non-final state. I'm sorry. This is Q4. The moment we have seen a 0, certainly we don't want to go back to any of the states, right? Because we have seen a 0. So this is the machine that will accept L complement, not L. Okay, so we're designing a machine to accept L complement first. So this is Q4. In Q4, because we have seen a 0 or 1, if you keep seeing more zeros and ones, we'll be stuck here. Now here, if you see a 0, we'll come here. Because anything except 111 or 111, we should come to this state. And the moment you come to this state, this is like a sink where you are stuck, right? So now if you notice, this has both 0 1, this has 0 1, 0 1, 0. What happens if you have 1 here, right? So what happens if you have 1 here? If you have 111, but what if you have 4 1s? In 4 1s also you want to come here. So now this is a proper deterministic finite automata that accepts LC. Now, how do you design a deterministic automata that accepts L but not LC? It's a very simple hack, right? So if you recall, let me do this way. Let me use a different color. All you do is you change the final states to non-final states and vice versa. So this becomes a final state, this becomes a final state, this becomes a final state. This is no more a final state, right? This is a non-final state. So let me just erase this and draw it. So Q2 and Q3 will become non-final states now. Q2 and Q3 will become non-final states now. So this is a finite automata that accepts L, right? Simple, am I right? Okay, so this is final, this is final, this is final. We made all final states non-final and vice versa, right? Now this is the deterministic finite automata that we got with 5 states, right? So some of you have said the answer is 4 states. Now, if the answer is 4 states, you should be able to merge 2 of these states. So we've explained in the course videos how to do that. There are 2 ways of doing it. One way of doing it is to draw the transition table and try to merge all the non-final states and try to merge the final states. Okay, there is also a graphical way that I've explained in the course videos, right? So again, if you try to merge these 2, look at this, try to merge states, right? If you try to merge any of these any 2 states amongst these 5 states, if you try to merge them, Again, the more detailed way of doing it is to draw the state transition table here and try to merge. Again, I'll show an example of that in one of the future problems that we'll encounter. But again, it's simple. You can't merge Q0, Q1. Pick any two of them and try to merge. You can't merge it. Again, you can do it visually also, right? If you try to merge these two, it will not work. Again, these are non-final states. Try to merge them. Okay, try to merge them, because the moment you merge these two into one state, look at this. Transition 1 should go to the same state, but transition 1 here is going to a different state. So you can't merge these two. Similarly, try to merge these two. Again, it will fail. In the state transition diagram, again, there are two ways of doing it. One using the state transition diagram and trying to merge these states, or using the DFA table. So if you try to do it, it will fail in all cases. So the right answer here is 5 states. You need a minimum of 5 states in a DFA that accepts this language. 4 will not work. I think some of you may have gotten a little confused, but just try it. Okay, sounds good. So let's go to the next question now. Okay. Again, very importantly, this graphical method that I have shown you without drawing the whole table is something that we explain with multiple diagrams in the course videos also. So those of you who are course registered can also check that out, because the visual technique is something that you don't find in many textbooks, but something that we do. Many of our teammates do that. Of course, the table-based approach is something that you learn in many textbooks, right? Again, we'll explain that in one of the future problems. Sounds good. So let's go to the next problem. I'm happy to see some of the students are also responding to follow-up questions by other students. Some of our mentors are also answering some of these questions. So yeah, very good. Again, it's impossible for us to answer all the questions in the chat window because it's a public session. In a private session, we might be able to do it because there is a finite number of questions. Here it's very hard. Okay, anyway, I see some answers here. What is the question? That recognize set of binary strings which contain 4 consecutive ones. Okay. Okay, some of you are saying B, some of you are saying C. No, so the question says binary strings. So, which means it's strings made of zeros and ones. So you have to read the question. There's a very good follow-up question that somebody asked. Are there only, does the alphabet only contain symbol 1? No, it says set of binary strings, which means it contains both 0 and 1. That's why you have to read the question carefully. Okay, I see a lot of answers. So let's go into the solution itself. Again, for many of these minimum number of states, one good strategy that many of our teammates employ is, while trying to construct the DFA itself, we try to avoid adding new states unless it is absolutely necessary. And we try to understand why a new state is needed. What is the logical intuition behind a new state, right? So let's go with that method. Again, there is another method which is first draw out the whole DFA and then minimize, but that takes more time in an examination setting. A question like this might be a 1-mark question where you don't want to spend more than 1 or 1.5 minutes, right? So let's try to construct it. So you want 4 consecutive ones. Again, it's a binary string, which means the alphabet consists of both zeros and ones. That's very important. Now let's go here. So you have Q0. You want to see 4 consecutive ones, right? So the moment you see 1, 1, So Q1 basically means that you have seen 1, 1, right? So Q2, right? Then again Q3, sorry. Then again Q3, okay? Then again Q4. So this basically says that you have seen 4 consecutive ones. So you go back here. So this has to be final state. But again, the diagram is not yet done. We are not yet done. What if, again, remember all that it says here is that the string must contain 4 consecutive ones, which means it could contain a 0 followed by 4 consecutive ones also. That's also okay. Which means from here, 0 should go back to the state. Again, this state logically is telling us that I have seen 1, 1. This state is basically saying I have seen 2 consecutive ones. This state is intuitively saying that I've seen 3 ones. This state is saying I've seen 4 ones. Now you have to use that intuition behind each of these states to construct a transition diagram, right? So now if I see 0 here, what should I do? Look at this. The moment we see 0 here, we should go back here because this is equal, because we want consecutive 4 ones. Remember, we want to see 4 consecutive ones. The moment I have seen a 0, that is equivalent, so I can't come to this state. This state basically says I've seen 1, 1 in the most recent character in my string, right? So this is, again, now if you're here, which means you have seen 1, 1. After that, if you have seen a 0, that is equivalent to going back here, right? Similarly, a 0 here will take you back here. Now, what about this? Now here, you have already seen 4 ones. So you have already seen 4 ones. After that, whatever you see, whether it is zeros or ones, doesn't really matter. So from here, the transition on both 0 and 1 is here. Now from every state, we have 0, 1. We have all the transitions, right? From this state, 0, 1. From this state, 0, 1. From this state, 0, 1. Now here again, you can argue the same methodology that you can't merge any 2 states here because we have been very careful in creating an intuitive understanding behind these states. Again, this is a very common mistake that people commit, that all you need is Q0 to Q4, which means you need only 5 states, right? You don't require the 6th state, right? So it's very simple. Again, gate questions for theory of computation are simple, and the options are also such that, again, I know some people who might have thought 4 is the answer. Okay, there are some people who would think 6 is the answer. These are very simple problems. If you're careful, you'll get it. Again, if you want to be really sure that this is the minimum number of states, you can again try to merge states. It will not work. Okay, sounds good. Okay, so let's go to the next question. This is a good question. Okay, I see answers already pouring in. Okay, please think through this. Again, there is an intuitive way to think about this also. I'll explain you that. Good to see some variance in the answers. Okay, so yeah, this is a very simple problem. There is also a very simple way of thinking about problems like these. Most of you got it right. So think about it. So what do we want? We want basically binary strings with an even number of zeros, and the number of ones is a multiple of 3. It's a and, not an or, that you have to be careful about, right? So if you think about it, if you think about logically, right, what should states imply, right? Imagine for every state you give 2 numbers corresponding to it, the modulo with respect to 2 and the modulo with respect to 3. So look at this, with modulo with respect to 2, right, which means it contains even number of zeros. The order of zeros doesn't matter, and the number of ones is a multiple of 3, which means, look at this, given any string, it can either contain 0, it can contain either even number of zeros or odd number of zeros. So if you look at modulo, right, I mean, this is one way to imagine this. So we'll create states such that you'll create a state like Qij, where I represents, right, whether this is even or odd. The j is basically the modulo 3, right? So if you think about it, the states can say 0, 0. So the 0, 0 basically means if you take the number of zeros, modulo 2 is 0. If you take the number of ones, modulo 3 is 0. So you need one state to represent 0, 0. And obviously this will be the final state, right? Because whenever you arrive at this state, look at this, whenever you arrive at this state, you know that the number of zeros is 0 and the number of ones is a multiple of 3, right? So from a modulo perspective, you can imagine that you need a state which conceptually has this property that you will arrive at this state when modulo 2 of the number of zeros is 0, modulo 3 of the number of ones is also 0. So how many such possibilities are possible now? 0, 0, 0, 1, 0, 2, because modulo 3 can take 3 values. Modulo 2 also can take 2 values, 1, 0, 1, 1, 1, 2. So your finite automata now, if you think about it, how will your finite automata look like? Again, let me draw the finite automata so that you're sure about it. So we'll have Q00. Again, this Q00 is what we start with. Q00 corresponds to the fact that the number of zeros modulo 2 is 0, the number of ones modulo 3 is 0. So this will be the both initial state and final state, because epsilon also has even number of zeros, right? Because 0 number of zeros and 0 is also a multiple of 3, right? So this is both the initial and the final state, right? Now look at this. Okay, so now I can create this Q10. So what does Q10 here represent? That, look at this, the number of ones modulo 3 is still 0, the number of zeros modulo 2 is 1, right? Look, the structure is very important. Now the moment I see another 0 from this, these two numbers represent these two numbers. That's the logical way to imagine this, right? And remember, it said and, not or. Okay, so you can draw a diagram like this. So from this, if I have, see, if I'm in this state, again, the first number represents 0, number of zeros modulo 2, the second number represents number of ones modulo 3. Now this logic is very, very useful to construct this diagram very easily. Anytime you're constructing finite automata, think about what a state intuitively represents. So this represents Q11 because this is modulo 0, this is 0. If it sees one more 1, it reaches here. Then if it sees one more 1, you go to Q12. Now if it sees one more 1, the modulo changes now. So you get a structure like this. Now if you see a 1 here, this go to Q01. Yeah, it goes to Q01. If it sees a 1, you go to Q02. If it sees a 1, you go back here. Now what about zeros? Look at this. So from this, if you start seeing zeros, we have the transition. If you see 0 here, what happens? Again, these states are representing the fact that the modulo 2 is, the number of zeros modulo 2 is 0, right? So if you are here, the zeros will take you here, this 0 will take you here, this 0 will take you here, this 0 will take you here, right? I hope I got all of it right. So 1, 2, 3, 4, 5, 6. Again, you don't have to draw the whole finite automata in the examination, but I'm just showing it to you for completeness sake. Ideally, if you know this logic that each state represents the number of zeros modulo 2, comma, the number of ones modulo 3, that intuition is sufficient to answer 6. And most of you got it right. Again, you can't merge these states because each state has a unique interpretation here. Okay, simple problem. I just wanted to explain you about how to think intuitively. Okay, so let's go to the next problem. Sorry. So this is the fourth one. Let's go to the fifth problem. Okay. Okay, this is the standard minimal equivalent DFA problem. Again, take your time, don't worry about it. I'm not putting a timer because it's getting harder. As soon as we see a bunch of students answering, I'll go into the answer. So don't worry about time, please go through it. Again, this problem can be solved both in 1 minute and 5 minutes. So take your approach, it's okay. When I see sufficient number of answers, I'll go dive into the solution. Again, the reason I'm doing it is right now time is not that important. Surely your timing will improve as you're coming closer to the exam. Okay, I see sufficiently good number of people answering. So let's see the answer, right? So I'll also explain the two ways of solving it, as I mentioned. Since I've already shown you how to do it visually by mixing these, let's do the other way now, right? So what is a transition table looking like? So Q0 is our initial state. Again, this is going to be slightly lengthy, but let's do it, okay, since we're anyway at it. Q1 is the final state. You have Q2 and Q3. So how do the transitions look like? Q0 on 0 is Q1, Q0 on 1 is Q2, right? So this is, okay, this is Q3, Q2, Q2 is here. So Q2 is Q3, Q0, this is Q1, Q0. So this is our state transition table, right? Now again, we know that you can't merge the final states and the non-final states. So let's try to be greedy here. One approach that you can do here is be greedy. So let's assume you have Q1 as one state, and what if you merge Q0, Q2, Q3, so 0, 2, 3, right? What if you merge these three? Basically what we're trying to do is, what if you merge these three? What happens then? Let's try to draw the state transition diagram now, right? So imagine you have Q1, which is obviously the final state, and you have Q0, 2, 3. Because Q0 is the initial state, so this will be the initial state. Now what happens here? Q1 on 0. Look at this. Q1 on 0 is going to Q3. So we'll just write Q0, 2, 3. Again, we are being greedy here. We are saying, okay, this is one final state. These are three non-final states. Let's try to merge them. A greedy approach, right? Now Q1 on 1. So what happens? Q1 on 1 is going to Q2. So Q2 is part of this Q0, 2, 3. Right? So Q0, 2, 3. So this is also okay. Now Q0, 2, 3, 0, 2, 3 on 0, where do they go? Look at this. On 0, where do they go? So this on 0 goes to Q1, but this on 0 also goes to Q1. Very good. But this on 0 goes to Q3. So when you're merging these three, what's happening? On 0, this is going here. On 0, this is going here. But this is going to itself. So that's what creates the problem. So you can't merge all three, okay? But where is the problem created? The problem is created because of Q2. So what if, the next step that we should do here is, what if we do it this way? Q1 is the final state. Let's merge these two now. The next approach, because Q2 got us into trouble, right? So let's keep Q2 as is. Let's combine Q0, Q3 into one state. Now let's see what happens, right? So you have Q1, Q03 and Q2, right? So again, Q1 is the final state. This is the initial state. on 0, 1. Okay, Q1 on 0. Q1 on 0 is going to Q3. So Q3 is part of this. So Q03. Q1 on 1 is going to Q2. So this is also cool. No issue still now. Q03. Now this on 0 is going to Q1, right? Q3 on 0 is also going to Q1. So that is good. So now we have no problem. You're going to Q1. Now what about on transition 1? This on 1 is going to Q2. This on 1, where is it going? It is going to Q0, right? So now if you mix these two, the transition has gone for a toss. So you can't merge these two also. You couldn't merge Q0, Q2. You couldn't merge Q0, Q3 also. You would not be able to merge Q2, Q3 also if you try it. Again, you can try that also. Again, the two ways of solving it. One way is to draw these tables. One way is to look at this from trying to merge this and see where the edges are going. Those are two ways of doing it, right? So for this question, the minimal equivalent DFA still will consist of 4 states. You can't get it to 3 or anything lower than that. So 4 itself is the answer here, right? Very simple question. Good. Okay, let's go to the 6th question now. The complement of this, okay. Please read the question carefully. That's very important. Okay, since most of you have, I've seen a lot of answers, so let's go to the solution, right? Again, look at this. Number of final states, the question here is not about the number of states. It's the number of final or the accepting states in the minimal DFA that accepts the complement of this language. So given this language, let's first try to construct the DFA that accepts this language. Then we know how to construct the DFA or the minimal DFA for the complement of it. So let's construct for this. So what does it say? It says W is either 0 star or it is 1 star, or this is important, right? So how do you do this? Look at this. So both of them will contain, so this will obviously accept epsilon, obviously, right? So the moment you get 0, that's cool. 0 is good, right? Because it's still in the 0 star part, right? So you go to Q1, right? So Q1 will also be a final state. And if you keep seeing zeros now, look at this. You have seen 1, 0. This is also final state. If you keep seeing zeros, just stay there. No problem. Now, the moment you see a 1, because 0, 1 is not allowed in this. Remember, 0, 1 is not allowed in this. This language will consist of epsilon, 0, 0, 0, 0, 0, 0, so on and so forth, and 1, 1, 1, 1, 1, so on and so forth. That is what is accepted by this language, right? So these are the words that belong to this language. So here we have it. Similarly, let's think about it. If you see epsilon anyway will be there. If you see 1, 1, that's perfectly all right. Right? If you keep seeing ones, that's also perfectly all right. But after you have seen some zeros, if you start seeing a 1, that's not allowed. Right? So you have to create another state to capture that concept. You have to do that. Right? So now what you have 0 and 1 here. So the moment you arrive at this is like a dead state or a sync state, because you have seen some zeros followed by 1. You have seen two different symbols, which is not allowed here. Now in this case, sorry, this is not final state. I'm sorry. This is a dead state. This is not a final state. Sorry, my bad. So this is Q3. Okay. Now similarly, if you're here and now if you see a 0, because you have seen ones only till now. If you see a 0, you'll go to this state. So this state is basically telling you that, okay, now I have seen zeros followed by 1, followed by some more zeros and ones, right? This says I've seen ones, zeros, and followed by zeros and ones, right? And that should not be allowed. So this is the finite automata. You can't shrink it any further. You can't reduce the number of states here, right? Because this state is capturing the concept of epsilon for you. This state is capturing all the other zeros. This state is capturing all the ones. This state is capturing all the cases which will not be accepted by this. Now to compute the complement of it, what do? All the final states become non-final states and vice versa. So in such a world, this becomes the final state. Right? If you want to build the minimal DFA for the language which is complement of this becomes the final, these three become the non-final. Right? That's it. It's very simple. So because this is the only final state, the answer will be 1. Very simple and straightforward. The common mistake that people commit is they don't read this question carefully. They think of it, okay, minimum states in minimal DFA, blah, blah, blah. They'll say, okay, 4 states. So they'll say 4 is the answer. So a lot of silly mistakes are because students do not read the question carefully, or they do not look at the options carefully. I think over half of silly mistakes just belong to this category. Okay, so we have to be slightly careful. Okay, let's go here. So somebody is typing in Hebrew and Arabic. Unfortunately, we don't understand those languages. English would be our preferred language of communication. Okay, I see a few options. Okay. Oh, there is a lot of variability in the answers. So think about it. If you have answered it in a hurry, just take some more time. This is a good one, actually. This is slightly tricky, but a good one. I see a lot of variability in the answers, so please double check your answer before we go into the explanation. Again, you can also eliminate some of the options. That's sometimes easier for problems like these. Think of counterexamples. Okay, since many of you have put in your answers, there is a lot of variability. Some people say A, some B, some C, some D. let's go into it. For problems like these, there are multiple ways of solving it. One of the easiest and more foolproof ways is to come up with examples so as to eliminate options. For example, look at this. Your S generates 0S, right? The S itself can generate 1t, so 0, 1t. Again, I've constructed this example after thinking through a few examples, okay? The t itself can be replaced by 1, so you have 0, 1, 1. Now, this example we have picked very carefully, right? So, while actually looking at these, I try to construct examples which will help me get rid of many options here. Look at this. This only contains, this is 0 plus or 1 plus because it's union, right? So this will contain 0, 00, 000, 1, 11, 111, etc. It will never contain 0, 1, 1. But this grammar generates 0, 1, 1. Look at this. S generates 0s. The S itself can generate again 1t. T itself can be replaced by 1. So this word is generated by this grammar, but certainly it's not generated by this expression here, right? So obviously this is not the answer, number one. Number two, again, this example is very useful. Thinking through this, because this example captures both this option, it also captures this. It's capturing a lot of nice things that are there in this grammar, right? Now, if you look at this, this is 0 plus, this is 1 followed by 1 plus. It doesn't, again, this language which is given by this expression also does not contain 0, 1, 1. It contains 0, 00, 000, or 1, 1, 1, 1, 1, 1, 1, 1, 4 ones, etc. It will not contain this. So this can't be the answer. Now let's look at the third option, right? So third option is slightly tricky. So the same example will not always work when you're trying to eliminate options. Again, here we have given slightly easier options for some of these. In the GATE exam, you could get slightly more tricky ones. Now, if you notice this carefully, this is 0, 00, 000. This is 1, 1 plus all of that stuff. That's cool. Look at this. What does this contain? This 0, 1 can be generated by this. 1, 0, 1, 1. But can 0, 1 be generated by this grammar? I'm asking the other way question. This expression, the language generated by this expression will contain 0, 1. But can 0, 1 be generated by this grammar anyhow? Think about it. So this is 0s. So you want to start with 0, but you want to have something else. So this has to be 0s. And s now I can replace either with 0 or 1t. What I want is 1. So I'll say I'll replace this with 1t. Now t itself does not generate epsilon. T can be replaced by one more t, right? Or with 1t. So since t does not generate epsilon, this language or this expression generates 0, 1 while this grammar does not. So option C can't also be an answer. The only valid option is D. This is by elimination. This is one way of thinking about it. The other way of thinking about it is, again, there is another way to solve this problem, which is if you just look at this part and this part. What does this say? Using these two, you can generate 0 plus. So you have 0 plus here. Cool. All of them have 0 plus. Now, if you notice, S generates 1t and t itself can generate 1t. This t itself can keep generating 1 or 1t. So because S generates 1t and t itself can generate 1 or more t's, you're always guaranteed to have 1t followed by 1 or more t's. So this obviously generates this, right? If you think logically. Now, so this option is certainly not ruled out. So either this. Now, if you notice this, look at this carefully. So S generates 0s. Look at this. S generates 0s. So which means you can have 0 followed by s. This s itself can generate 1 followed by t. And you know t can generate more ones. So if you think about it, you have 0, 1 followed by 1 plus. Because this t can generate 1 or more ones. So if you think about that logically, this third part also will make sense. So there are two ways of solving it. One is eliminate by constructing counterexamples. The other is think about all the options that are given. So 0 plus is very simple to understand. 1, 1 plus is also very simple to understand. 0 plus 1, 1 plus is also easy to understand if you think carefully. If you think carefully, you'll clearly rule this out. right? So that's another way of thinking how to arrive at D. Okay, slightly tricky, but a very good. But again, most gate questions are easy, so you don't have to worry about it. Okay, let's go to the 8th question now. We'll move slightly fast now because we have many more problems and we want to finish it by 8:30. Again, use counter examples even in this problem. Be slightly careful. This is a simple question, so even if you just read the question carefully, you'll be able to answer. Okay, so most of you got it right. I think 1 or 2 of you got slightly confused. Now let's look at this. Very simple. This is a dead state or a sinc state. Let's not forget that, right? So this is a final state, final state, final state. So all strings of A's and B's over the alphabet, no. So if you have B, A, B, you've reached a dead state. So B, A, B is all the strings that are generated by the alphabet which consists of A and B, but it will never be accepted here. So A can't be the answer. All strings of A's and B's such that every string contains a substring BAA. So the moment you have BAA, so you have BAA, okay, but what if you have BABAA? Let's think about this, right? So you have BABAA. This contains the substring BAA. Look at this. All strings of A's and B such that every string contains BAA. So I just constructed an example where you have BAB, you have arrived at the dead state, then you have AA. Now this string contains BA as a substring, but you have arrived at a dead state which is non-final, which means it will not be accepted by this machine, right? So obviously B is also incorrect. Now see, all strings of A's and B's such that every string does not contain the string BAB. This seems logical, right? Because the moment it has this string BAB or substring BAB, look at this, BAB. The moment it encounters BAB, we are taking it to a dead state and we are never coming out of this. So this seems to be the most logical thing. So this is one potential answer. Let's look at option D. Always read all the options when you're eliminating or even in general. So don't skip any option. This says A star union B star. Now again, look at this. String AB does not belong to this expression, does not belong to the language generated by this expression. This is A star union B star. But if you notice, AB is accepted by this machine. So obviously this can't be the answer. And this sounded most logical, right? And obviously we have eliminated ABD, so C is the right answer. Very simple question. Okay, let's go to the next question now. Again, this is a simple question. Try to eliminate options, you will get it. TOC is extremely scoring in gate. Okay, most of you got it right. One or two of you may have slightly gotten confused. Again, think about it logically, right? So this accepts epsilon, this also accepts epsilon because you have a star. And if you think about it, this is saying strings containing a with even number of a's. That's what this means, right? A star basically says epsilon, a, 4a's, 6a's, 8a's, etc. This basically says odd number of a's. So you're accounting for both even number of a's and odd number of a's and also epsilon. And this should be same. So 1 has to be the answer. The moment you say 1, see 1 is correct. Again, this question says which of the following regular expressions represent the same language. Certainly 1. Right? The moment you say 1, this can't be the answer. You're eliminating options. Now let's look at 2 now. Okay. It says a star, b star. Right? So epsilon is also there. Cool. A plus b star, ab star. Oh, this is tricky because if you look at this, this can only generate AAB, BBB. Bunch of A's followed by bunch of B's. It could be epsilons also. Now this on the other hand, look at this. This on the other hand, because you have A or B star, right? It has A or B star. It can generate AB, AB, AB also. And this could be epsilon. Now something like AB, AB, AB can never be generated by this expression. So obviously 2 is incorrect. So the moment 2 is incorrect, you also can start eliminating. This can't be the option now. This can't be the option. So you're only left with option C. You don't even have to go into understanding this. Well, it's simple to understand. What does it say? It says starting with B. So just get rid of this B. What does this say? A star, B star followed by A star. Again, you can easily understand that this and this are equivalent. Again, you don't have to go into all of that, right? If speed is important, because a question like this might just be asked for 1 mark. Because you can eliminate options very easily. C is the right answer. It's very simple, right? Sounds good. Oh, this is a tricky question. I'm telling you right away that this is a tricky question. So be warned, I'm telling you upfront, this is a tricky question. And read the question very, very carefully. Yes, somebody is asking in option 3, do you have xy belonging to sigma star? Sigma is the alphabet, right? The capital sigma. It's not epsilon, it is sigma. Okay, I've seen answers from many of you. Some of you got it right, some of you are slightly confused, but it's a good question. Again, we set this question based on a very recent GATE question actually. Let's wait for a few seconds before we jump into the solution itself. Okay, so let's get into it, right? So every subset of a regular language is regular. That's obviously not true. Because look at this, a power p, where p is a prime, is obviously a subset. This language is obviously a subset of a star, right? It's a subset of a star. A star consists of all the strings with a. A power p is a strict subset, but we know that this, we've also discussed this in the first problem. We know that this is not regular. So obviously this is false. Again, the question says which of the following are false. So certainly one has to be in the answer. So you can eliminate this option. Okay, eliminate this option. So it has to be A, C or D. Now let L dash, okay, let's go into this. So this can't be the answer. So L dash equals to L1 intersection L2. If L dash is regular, so we know that this is regular, and L2 is regular, we know that this is regular, then L1 must be regular. Not always true, right? So let's build a simple counterexample to this. Imagine if this is epsilon. Epsilon is regular, right? Anything intersection, say the language only consists of epsilon, empty string, it is regular. Anything intersection this is also epsilon, so this is also regular. Now here in L1, I can just put a power p where p is prime. So here, look at the statement here. L dash is regular, L2 is regular, but L1 is not regular. So 2 is also incorrect. So 2 also has to be the answer. Okay, so this can't be the answer now because it has only 1 and 3. So the final thing comes down to either option A or D. That's where most of you are, right? So you've eliminated B and C. Now this question is based on a very similar question that was given in GATE 2020. This option, very similar. Lot of people, as soon as they look at it, they say, hey, you have reverse of it, so we should use a stack, and hence this should be some context-free language. But this part is the trick. What does it say? It says, again, this is a very good question from GATE 2020. I think one of the best questions I've seen in GATE 2020. What does this say? This says, y is not a single character. Y is not even a fixed string. It says x comma y just belongs to sigma star. X and y can be any string in sigma star. It can be any string. Remember, y is not constant. Remember, y is not constant. What we learn is, suppose if the language was, let's say, W, C, W, R. Okay, so where C is a constant alphabet, a constant symbol, right? Such that W belongs to sigma star. Again, when we learn context-free languages and context-free grammars and push-down automata, we learn that this is deterministic context-free language, right? Because I'll keep pushing till the time we encounter C into a stack, and then I'll keep popping and matching. That's how we implement it in DCFLs. Similarly, imagine if you have a language like this, W, W reverse, such that W belongs to sigma star, right? This we have learned is you can build a non-deterministic context. You can build a non-deterministic PDF for this because you don't know where to stop pushing and where to start popping. So you can. It's a context-free language. So because we've seen these examples with DCFLs and CFLs, many people, the moment they see this, again, remember here that C is a symbol. C is a constant symbol here, right? The moment they see this, it's very easy to fall into the trap and think, hey, we need a push-down automata for this. But it's not, because, okay, that's the most interesting part. Imagine there is some W, some word that belongs to L, language generated by this regular expression, by this L, let's just say L, okay. Suppose if there is a word that belongs to L, some word, it could be any word, we don't care. Now, given this word, you can write this word itself as word, the whole word. Again, remember that W belongs to sigma star. Okay, so let W belongs to sigma star, and also W belong to L. So W is a string made of all the alphabets you have, all the symbols that you have, and it belongs to L. The moment you give me W, I can add an epsilon here, and the reverse of epsilon is also epsilon. Now, if you look at this, what does any word that belongs to sigma star, I'll argue that it also belongs to L. The reason being, given any word, I can place epsilon here and epsilon here, and we can imagine that this is X, this is our Y, and this is our X reverse. Because remember, X and Y belong to sigma star. So if you give me any word that belongs to sigma star, right? Any word that belongs to sigma star, I can decompose this word into the word itself with an epsilon prefix and an epsilon suffix. Now this will also belong to this language, because X and Y, remember, X and Y are some strings that belong to sigma star. So this language that is represented here, this language L is equal to sigma star itself. And we know sigma star is regular because it accepts all the strings that are there. So this option is correct. These two options are incorrect, right? Very importantly, right? So what do you have? You have 1 and 2 as the incorrect options because the question says which of these are false. Again, this is very tricky question. It's a very good question that was asked in GATE 2020. So we try to create a question based on that, right? Very good question actually. Okay. Again, I think this is, to be honest with you, I think this was the best question that I have personally seen in GATE 2020 and probably in all of Theory of Computation in the last 5 years in GATE. Okay, let's go to the next question now. Again, try to eliminate options if you can. Again, remember, this is an NFA. Many of you might get confused. This is a non-deterministic finite automata. Be very careful when you eliminate options because there are a couple of tricky ones here. Again, many of you are making mistakes, so please rethink. I see a lot of mistakes. Intentionally, we have given slightly tricky questions, so please be careful. Okay, some of you made silly mistakes at the beginning. Hopefully, many of you realized it as soon as I requested you to correct. Thank you. That's good. So let's start eliminating options. Sigma star. Obviously, this is no brainer because think about it. If you have BA belongs to sigma star, but BA will not be accepted by this because you have B, you don't have a transition here. So obviously, this is not the answer. That's like straightforward. Now look at this. This has A power n, B power n, C power n greater than or equal to 0. Now, what if you have, let's say, this is your starting state, right? So, what if you have a string BC? See, BC has B power 1, C power 1, A power 0. Look at this. This string is accepted by this because this is a starting state, B, C. This is a final state. So, this is accepted by this machine, but this is not part of this language. So, obviously, option B is also incorrect. Okay. So you're eliminating A, you're eliminating B. What about option C? This is the tricky part where many of you made the mistake. Okay. So think of some example here. So it says M and P can be greater than or equal to 0. What if M, N are 0? Because look at this whole thing here. If m and n are 0, what happens? If m equals to n equals to 0, and let's say p equals to 1, let's just say, then what happens here? You have a power 0, b power 0, c power 1, which means this will be just c alone, right? So a power 0, b power 0, c power 1, this is c. But will this machine accept c? No, it won't accept c, right? So obviously this can't be the answer. So by eliminating these three, it's very simple to see that D is the answer. But there's another way also of thinking about it. Look at this. First, if you notice, epsilon basically says, because this is the initial state and also the final state, will accept epsilon. Then it says a power m, where m is greater than or equal to 0. This loop here basically represents a power m, right? Again, this is the starting state. So b power m, okay, so it says b power n, where n is greater than or equals to 0. Okay, so this accepts 1b, 0b's, 2b's, etc. So this state will capture this part. Now what about this here? A power m, b power n. So any number of a's followed by a b. Okay, what if you have a power n? Oh, a power m is already taken care of. So it can also act this union this, union this. Look at this, a power m, any times a, then b power m, b power n, sorry. Because a could repeat a number of times, b could repeat a different number of times. Now what about this? This says a few repetitions of a few repetitions of b, and a few repetitions of c. It just requires that this and this should be greater than or equal to 1. That's all it's saying, right? Because you need 1b to arrive here, 1c to arrive here. So you can also think logically. Elimination is sometimes easier, but even if you think from first principles carefully, you'll see that D is the right option here. Both ways you can solve. Okay, sounds good. So, okay, my mouse is giving me a hiccup. Just let me turn it off and turn it on. Just give me a sec, guys. My mouse is troubling me. Okay, it's back. Okay, so, okay, 12th question. The equivalent regular expression for this DFA. Okay, cool. Again, you can either do elimination or construct it from first principles. I see a lot of people who are trying to answer fast make mistakes. Again, accuracy is actually more important than speed for gate, right? So please don't be in a hurry to solve a problem. Think through it. Getting it right is important. Speed will automatically be built up as you practice thousands of problems. Okay, so most of you got it right. So let's get into the solution, right? So obviously, let's go step by step, right? So you can eliminate, or you can go first principles, right? So let's start eliminating, okay? Because that's one of the easier ways. So this has B or AB star, right? So for example, you don't have BA in this expression, but this machine accepts BA. Look at this. This machine accepts BA, but BA will not be there in this expression. Will not be generated by this expression. So obviously this is incorrect. Okay, let's take BA itself. BA is accepted by this machine, right? BA, yes. Can BA be generated by this? Again, the trick here is to think of an example like BA. Now, is BA generated by this? No, it can't. So B or AB or AA star B. So you can't generate it. You can't generate B with just a single A after that, even though there is a star here. You can generate BAB with this, but not BA. So obviously this also can't be the answer. Now let's think about this. Can you generate BA with this? Yes, you can generate. So because you have B star here, BA can be generated. So the same example won't work. Let's think of another example here. So in this example, what do you have? You have suffix A, right? So imagine, okay, so this language accepts BB. Okay, so this machine accepts BB. Okay, BB it accepts, but here BB will not be accepted by this, because you need to have A as a suffix. Mandatory A is required. So BB is accepted by this machine, but it is not generated by this regular expression. So obviously this also can't be the option. The only option you are left with is D. Right? So that's the elimination process. The other way to think about it is this. Look at this is the final state, B star. So you have the B star. Okay, then you have AB. Look at this, all the transitions that are leading to final states, AB, obviously AB star. Then look at this, you have A, then some A star, B can also take you to final state. Look at this part, A, some number of A's after that, you'll stay in the same state, then B will also take you to the final state. And any repetitions, star basically means 0 or more repetitions of what you have here, right? So it will all take you to final states. Or look at the second part of the story. B, any number of repetitions followed by A. Any number of B's followed by A will also take you to final state. So this whole first part was trying to capture all the expressions that lead to Q0 as the final state. The second part is trying to capture all the cases where Q1 is the final state. Look at this. Any number of repetitions of B followed by A will take you here. Then A, B. Look at this. A, B. You can do this loop as many times as you want. But finally, if you see A, because there is the suffix A here, it will take you to a final state. Cool. So this is also understood. The third case, you have A, any number of repetitions, B followed by A. Look at this. A star B. A star B followed by A. There is the suffix A. Let's not forget that suffix A. So this A will take you to Q1. So this expression corresponds to Q0 as the final state. This expression corresponds to Q1 as the final state. That's another way of thinking. Elimination is one option. Trying to understand what each state represents and how these expressions are constructed is the other way. Right? Simple problem. So D is the right option here. Okay, so let's go to the final 13th question. Okay, so let's answer this. Please read the question very carefully. It's a simple question. If you read the question carefully, it's a simple question. Okay, I see a lot of students putting in the answers, some confusion here and there. So just please revisit the question Many of you are getting it right. Some of you are messing it up. So just read it carefully. It's a simple question. Okay, so let's get into the solution itself. It's a simple problem. Look at this. If you look at this expression, what does it say? It says you need, contains, look at this, contains at least 2 A's. At least 2 A's, because you can get more A's here. So it contains at least 2 A's. So what does this expression say? Greater than or equal to 2 A's. At least 2 A's. And the union basically means or. And what does this expression say? This expression says exactly 2 B's. Because this is A star, this is A star, this is A star. This is exactly 2 B's. Exactly 2 B's. This is at least 2 A's, because there could be more A's generated by this. So if you read through all the options, this is the most appropriate option. Contains at least 2 A's, that's what it is, or exactly 2 B's. So option C is the right option. Very simple. Again, just wanted to just explain something quickly. So the reason some of you are asking for more sessions on different topics. So what we're trying to think of here is this. We will go through each of the subjects. See, we have already done data structures and algorithms. We have done some overview of C. Now we are doing TOC followed by CD, all bunch of subjects. Now once all the subjects are over, we will revisit this order. Again, the reason we have done only one session in C is because we are giving weightage based on marks. Okay, so we'll keep revisiting. We want to do this loop multiple times, so that if you're studying TOC now and you have answered these questions, again, once we finish this loop, again, we want to redo the whole loop again. We want to redo the whole loop again and again and again. So think of these problem solving sessions as revision plus problem solving. We want to do this multiple times before the gate exam. Obviously, as we come closer and closer to the gate exam, we'll do these sessions in such a way that whole of data structures algorithms will be one day, whole of C will be next day, whole of TOC will be the day after that, and so on and so forth, right? So that's one. Somebody is asking for a 3-hour session. We do not want to do it because there is a lot of scientific evidence that shows that people for more than 90 minutes, you can't get them to focus, especially in a session like this. Our objective is not just problem solving. Our objective is also that we explain the solutions, especially for those who couldn't figure out the solutions, right? So we believe most sessions will be 60 minutes. There might be one odd session which is 90 minutes, but most likely all sessions will be 60 minutes. And of course, we are taking good chunks. For example, in this session, we have covered literally 50% of the weightage of TOC. We'll conduct one more session for TOC where we'll try to pack up all the other topics. So that by doing 2 or maybe 3 sessions for every subject, we can iterate through the subjects faster. We also have a few general sessions, some guest speakers coming in, right? So we want to finish these loops faster so that we can do more practice. Okay. Thank you very much, folks. Thank you for joining in today evening, and thank you for the 90-minute session. Thank you very much. Bye-bye.